Hello and welcome. Today, we're going to dive into the greenhouse effect. The fundamental reason our planet isn't just a frozen chunk of rock floating in space. We're going right back to the basics to really understand how Earth keeps its temperature so perfectly tuned for life. So let's just start with a big question. Think about it. If the Earth didn't have an atmosphere, it would be a completely frozen wasteland. We're not that far from our own moon, which is basically an airless, frozen rock. So what's saving us from that same fate? What is this invisible, life-saving blanket that our planet has?
And wow, the numbers really tell the story here. The difference is just staggering. Without our atmosphere, the average temperature on Earth would be a frigid minus 18 degrees Celsius. That's 0 Fahrenheit. That's below freezing everywhere, all the time. But with our atmosphere, we get this comfortable average of 15 degrees Celsius or 59 Fahrenheit. That 33-degree difference is, quite literally, the reason we're all here. So how does that even work?
Well, to really get it, we need to follow the energy. So let's trace the path of a single sunbeam on its incredible journey from the sun all the way down to Earth.
Okay, this right here. This is the absolute key to understanding the whole thing. The energy coming in from the sun is mostly shortwave energy, basically visible light. But the energy radiating back out from the Earth is longwave infrared radiation, or what you and I would just call heat. And that one simple difference changes everything.
And you can see just how much of that incoming energy is plain old visible light, a whopping 43%. It's the very same light that lets you see everything around you. And it turns out our atmosphere has a very specific reaction to this particular kind of energy.
And that reaction is basically nothing. This is one of the biggest misconceptions out there. The sun doesn't really heat the air directly. Instead, for visible light, our atmosphere acts just like a clear window, letting most of that energy pass right on through without absorbing it.
So if the sun isn't heating the air, what is? Well, the answer isn't up in the sky. It's actually the ground right beneath our feet. The Earth itself acts like a giant, planet-sized radiator.
It's kind of like a simple three-step dance. First, that shortwave solar energy we talked about just zips right through the atmosphere, no problem. Second, the ground, all the land and all the oceans, it just soaks all that energy up. And then for the third step, the ground re-releases that energy, but now it's been transformed into that long-wave infrared heat.
So the crucial thing to remember is this. The atmosphere is heated from the ground up. The Earth's surface is the radiator for the whole planet. And this explains something you've probably experienced. It's why it gets colder when you climb a mountain. You're literally just moving farther away from the radiator. It's a really powerful and kind of counterintuitive idea.
Okay, so the Earth is radiating all this heat, but what stops it from just, escaping out into the cold of space? This brings us to the main characters of our story, the special gases that create the atmosphere's heat trap.
So remember how the atmosphere is transparent to the sunlight coming in? Well, it is definitely not transparent to the heat going out. Certain gases are fantastic at absorbing this long-wave heat radiation, and the two heavy hitters here are water vapor and carbon dioxide.
Now get this, of all the heat being radiated by the Earth, about 60% of it is absorbed by just one of those gases, water vapor. It is by far the single most important greenhouse gas when it comes to keeping our planet's thermostat at a comfortable level.
But not all of the heat gets trapped. See, there is this special little range of infrared energy, a very specific wavelength that none of these gases are very good at grabbing. Scientists call this the atmospheric window. You can think of it as a natural escape hatch that lets some of the Earth's heat vent directly into space, which helps maintain a really delicate balance.
So what happens to this little escape hatch when it gets cloudy? Well, it's pretty simple. You can think of clouds as being like blinds for that atmospheric window.
And what do blinds do? They block the window, right? Clouds are amazing at absorbing that heat that's trying to sneak out through the atmospheric window. They catch it, and then they radiate that heat right back down to the surface. And this is exactly why clear nights get so much colder than cloudy nights. The blinds are closed, keeping all that warmth tucked in.
Okay, now we have to talk about the biggest point of confusion out there. You hear the phrase greenhouse effect, and I bet your mind immediately jumps to a problem, to something bad. But it is so important to separate the natural process from the human-caused changes. So let's be perfectly clear. The greenhouse effect itself, the one we've just been describing, is a completely natural and essential process. Seriously, without it, the Earth would be frozen solid. It literally makes life possible. Global warming, on the other hand, refers to the enhancement of that natural effect, something caused by human activities that add more heat-trapping gases to the air, which, in turn, leads to a lot of undesirable changes.
You know, one of the sources we looked at put it perfectly. One process makes life possible, the other involves undesirable changes. They are not the same thing, and confusing the two is just a fundamental mistake when you're trying to understand the science here.
And if you want to see what a runaway greenhouse effect looks like, all you have to do is look at our next-door neighbor, Venus. Its atmosphere is 97% carbon dioxide. This adds an unbelievable 523 degrees of extra greenhouse heating, creating a surface hot enough to actually melt lead. It's a pretty stark reminder of just how powerful this effect can be.
All right, so let's bring this all together. What's the big picture? What's the main thing to take away from all this?
It's really all just a planetary game of pass the hot potato. High-energy sunlight passes right through the air like it's not even there. The ground catches it and heats up. Then it tosses that energy back up as heat, and the greenhouse gases in the atmosphere catch it and toss it back and forth, keeping our world warm before that heat eventually escapes.
And that really brings us to our final thought. The greenhouse effect is this incredibly fine-tuned natural system that has created the world that we all know and love. It maintains a very delicate balance. So the question we're all left with is, by adding more players to this game of pass the hot potato, how exactly are we changing the rules? And what will that ultimately mean for the balance of our planet?